Welcome back to part 2 of the video for section 8.1 on systems of equations and Gaussian elimination. If you recall from the first video, I mentioned that I'm kind of changing a little bit of what's done in the textbook. I'm taking some of the ideas from section 8.2 and putting them into section 8.1 just because I think it's an easier approach to these problems. Let's go ahead and get started with this. We're asked to solve this system of equations, and I'm just going to give you a heads up. This system is a consistent independent system. So it's a consistent independent system. If we look back 2 slides previous to see what that term means, a consistent independent system has one solution. So we should find one set of x, y, and z values that make this system, that are the solution to this system. The other thing I'm going to do at the end of the problem is I'm going to write it in triangular form. The definition of triangular form is in the notes. I'm going to do that because WebAssign asks for that for, I believe it's the first problem. Okay, so let me get started here. The first thing I'm going to do is I'm going to rewrite this system of equations with only the coefficients and the constant. And here's how I'm going to do that. The first equation is got a coefficient of 1 for x, 1 for y, -1 for z. That looks terrible. You deserve better. -1 for z. And then I have a constant of 9. The second equation doesn't have an x, so that has a coefficient of 0 on x. And then it has a coefficient of 1 for y, 3 for z, and 3 for the constant. Again, folks, those are terrible. 3 and 3. There we go. The final equation has a coefficient of -1 for x, 0 for y because there is no y variable, and -2 for z. And then the constant is 2. Now, to make this look a little fancier, I'm going to just go ahead and kind of box it in here and here. And then I'm going to put this little vertical line right here just to identify the difference areas between the coefficients and the constants. And remember, everything in this column is an x coefficient, everything in this column is y, everything here is z, everything here is a constant. And I'm going to call this row 1, row 2, and row 3. Okay, if you recall from the previous video, my goal is to get everything down this diagonal equal to 1 and everything in this corner equal to 0. Well, I almost have all the zeros. I just have to turn this -1 into a 0. But I don't have all 1s across this diagonal yet. So let me show you how we're going to do this step by step. Okay, the first thing I'm going to do is try to get rid of this -1, and I can get that by adding row 1 to row 3. And that's going to be my new row 3. Row 1's going to not change. Not doing anything to that yet. Row 2 is not changing. I'm not doing anything to that yet. But my new row 3 is going to be row 1 plus row 3. So I have 1 plus -1, that gives me 0. I have 1 plus 0, that gives me 1. I have -1 plus -2, that gives me -3. And I have 9 plus 2, which gives me 11. Again, that's an 11. So right now I want to address one burning question that I'm sure some of you have. Why on earth am I allowed to do this? Why can I take row 1 and add it to row 3? Well, if you recall our discussion of the elimination method in class the other day, we said you can add anything you want to both sides of an equation as long as they're equal. Remember, row 1 just represents this top equation right here. And row 3 just represents this equation right here. If you look, when I add x and -x, they cancel. The x variable is eliminated, so I now have this 0 here representing a new equation for this row that has no x variable or a coefficient of 0 on it. The next thing I'm going to do is try and get rid of this 1. The way I'm going to do that is by taking this row 2. I'm going to take the opposite of row 2 and I'm going to add it to row 3. Okay, and that's going to give me the following table of coefficients and constants. Row 1, unchanged. Row 2, unchanged. Row 3, now I'm going to take the opposite of 0 and add it to 0. That's 0. The opposite of 1 and add it to 1. That's 0. The opposite of 3 and add it to 3. That'll be negative 6. The opposite of 3 and add it to 11. That'll be 8. Okay, so where am I at now? Our goal is to get 1s down this diagonal and 0s in the corner. Well, I got the 0s in the corner part. Now I just need to work on 1s in a 1 in this row right here. In order to get a 1 in this position right here, what I need to do is multiply row 3 by negative 1/6. He's writing with the highlighter, folks. Negative 1/6 times row 3 will do that for me. And again, row 1 and 2, unchanged. Row 3 is going to change. 0 times negative 1/6 is 0. 0 times negative 1/6 is 0. Negative 1/6 times 6 is positive 1. Negative 1/6 times 8 is negative 8 over 6, or negative 4/3. So I've achieved my goal. I've written this system of equations. I've used Gaussian elimination to get 1s down the diagonal. Be consistent with colors, that should be yellow. 1s down the diagonal and 0s in the corner. Okay, so the next thing I'm going to do is I'm going to take this just table of numbers and write it as a system in triangular form. Here's what it's going to look like. My first equation is going to be x plus y minus z equals 9. Where do these values come from? My table of coefficients right here. My second equation, it's going to be 0x, so I'm not even going to write it, plus 1y plus 3z equals 3. My last equation is 0x plus 0y plus 1z equals negative 4/3. So this system is now written in triangular form. What I can do is I can use z equals negative 4/3 and substitute back into this equation to find y, and then both of those values back in this equation to find x. I'm going to go ahead and pause the video and do that now. And again, this all starts with z equals negative 4/3. So rearranging this equation to y equals 3 minus 3z, then substituting in negative 4/3 for z, I get y equals 7. Now I'm going to do the same procedure up here with this top equation. I'm going to substitute in my z equals negative 4/3 and y equals 7 to solve for x. So substituting my values of z equals negative 4/3 and y equals 7 back into this equation gives me the solution x equals 2/3. The last thing WebAssign will ask you for is to write this thing as an ordered triplet. So we're going to have x is 2/3, y is 7, and z is negative 4/3. And that is the solution to this system of equations. You can now go to part 3 of the video where we'll look at a different system that is example 2b from the notes.